have no idea.
Okay, today learning target, I can differentiate inverse trig functions. Okay, we continue to go through all the different types of functions and being able to find the derivatives of those functions. Inverse trig is kind of something different. We haven't talked about these yet. I want to refresh your memory on inverse trig here to begin with. Okay? Oh yeah, still all the same. Yep. Still in the derivative, so we're talking probably, there's some chain rule here, so probably this will fall on a C8. Could show up again somewhere on an implicit, so it could be falling to C10. They're all kind of derivatives.
How many times are we taking C8?
Okay. I don't know.
Yeah.
I know one more time for sure.
So would that make it 3?
I don't recall. Let's focus on this right now. We're off task. Let's go. For instance, you may have seen it written this way. Maybe you've seen it written as sine to the -1 of x. That's the way it is on your calculator. Okay, but that is an inverse sine function. The graph of it looks something like this, where here's 1, here's -1. Here's pi over 2, here's negative pi over 2, let me think here. The inverse sine of 1 would be a positive pi over 2, this would be here, so then the graph would look something like this. Okay? A lot of times this would be capitalized.
Oh, that's why.
That is the graph of the inverse sine function. You know what the sine function looks like. If you don't, here's a little refresher on that. Okay, basically here, and so on. Okay, where it goes up to 1, down to -1. That's a quick little rough sketch. So the inverse sine, all right, the inverse sine helps you figure out the angle whose sine value is something. Okay, so if I plugged in a 1 for x, if you see arc sine 1, what you're trying to figure out is what angle has a sine value of 1. The answer, pi over 2. So that's why when x is 1, y would be pi over 2, because the inverse sine of 1 would equal pi over 2. If I plugged in a -1 for x, the inverse sine of -1 would be negative pi over 2, because the sine of pi over 2 is equal to -1. Okay? Now, yeah, there are infinite number of answers to these. I mean, if I say inverse sine of 1, what angles have a sine value of 1? Well, 90, 450, 810, okay? You can keep going and going and going, okay? But we only ask for an answer that's somewhere between negative pi over 2 and positive pi over 2, or between -90 and positive 90, because every answer falls somewhere in that interval. Yes?
So is it essentially the same graph just flipped like this?
In a sense, because on inverse functions, x's and y's just trade.
Okay.
Just flip. Okay? So yeah, it is, in a sense, flipped.
Or not flipped, twisted.
Yeah, I know what you meant. I know what you meant. So, you don't need to know how to graph it. I'm just refreshing your memory on what the graph of it looks like and what an inverse sine function tells you. Inverse sine functions tell you values, or excuse me, tells you the angle whose sine value is a certain number. Okay? So, that's a quick review on that. The derivatives for all of your inverse trig functions are on page 376. What I want to do is, first let's just say, we'll write those out. Take the time and write those out, okay?
Instead of u, can we use x?
I'd use u because you're more than likely not just going to have arc sine x, so you're going to have to use a chain rule. So I'd just write it with the u, okay? So we'll write those all up. By when they say u prime, they mean du, really. We're on page 376 again. We'll write down all of our derivatives.
So, is there a way to relatively easily solve this out the same way we have for our other trig ones?
What do you mean?
Well, like, for finding the derivative of the tangent or of secant or cosecant, then we can just use the rules that we already have to solve it, or will we actually have to memorize all of these?
I'm going to show you the proof of the sine, okay? And I mean, I can show you proof of the cosine too, but the proof ends up being very similar. Once you know sine and once you know cosine, tangent's pretty easy to get to. Arc cotangent would be pretty easy to get to. Right off the top of my head right now, I'm looking at the arc secant and arc cosecant, and I don't quite see the proof in that mentally, how I'd come up with those, but I haven't given it a ton of thought right now either.
All done. All done. You were.
Wait, what? Oh. It's like, what is he not done with? Then I realized, oh, he doesn't.
Go ahead and do an example here.
I'd love to do an example.
The kind of enthusiasm we need.
Must we start with this? Just want this also with this or
Alright, there you
triangle
go.
in it.
You're welcome.
Wait.
Does the book have the proofs of those?
In the back there might be one. I'm going to do one with you. Looks like they saved some of the proofs as an exercise. So
would it be?
it would be, like I said, I haven't sat down to figure out all the other proofs. Probably be helpful to have a answer book to make sure we were doing them right, but like I said, I can give it some thought if I have time here. Alright, so let's find the derivative of this. So y prime would equal, if you follow your arc sine rule, this is essentially your u. So if u is 2x, then u prime would be 2, right? So following your rule, u prime is on top, so 2 over, what's in the denominator?
Square root.
Square root of?
1 minus 2x squared.
1 minus the
Wouldn't it
value
be
of 2x squared, or 1 minus 4x squared then?
And then, is the reason it's like that because it's the same as 1 over the square root of 1 minus 4x squared times 2?
Correct, yeah.
Okay.
Yeah, a lot of times it's just 1 over this times du, or
Mhm.
times u prime.
But
and
it's
we
our,
just-
okay,
We just went ahead and put it on the numerator.
that makes things simple.
Okay, so pretty easy there. We'll do another one here. Let's go arc cosine square root. Arc cosine of square root x. Try that one out.
Oh, that's not. That'll just be-
Another one for you.
Really? I think so. I don't know.
So again, if it helps, so u equals x to the 1/2, or u is the square root of x, right? So what would u prime be then?
1/2 x to the negative 1/2.
Good, 1/2 x to the negative 1/2. So therefore then y prime,
Negative 1/2.
what goes on top?
Negative 1/2 x.
Negative this, okay,
Yeah.
yep, sorry. Nice, if you said that, I didn't hear you.
What? Oh, never mind. This is-
Over,
I do.
you could, yeah.
You don't have to.
I'm just making it very
Sequential.
perfect right as the formula is written. I'll probably simplify it then, but yeah, absolutely. And then what is it? 1 minus u squared?
Yep.
So 1 minus what?
X.
X.
And then wouldn't you probably want us to put the 2 on the bottom and then the x on the
Yeah,
bottom?
I would probably go a little further. Move this 2 down to the bottom. Keep the negative 1 on the top. You can move that down to the bottom as well.
So would it just be 1 over 2 square roots of x minus x squared?
So if you move the things down, if you move x to the negative 1/2 down to the bottom, it becomes x to the positive 1/2 on the bottom, which is square root x. Now you could go even a step further and you can multiply the 2 square roots together. The square root of x times the square root of 1 minus x would be the square root of x minus x squared. The square root of x minus x squared. So really, you'd have 2 times the square root of x minus x squared. Because you can multiply what's underneath the radicals together if they're both under the same type of root. And since they're both square roots, I can multiply x times 1 minus x. No, because that's a subtraction in there and not a multiplication.
It would be like trying to affect when they're not both x squared or just x.
Say that again.
Never mind.
Okay. All right, and then arcsecant of e to the 2x. So arcsecant, again, let u be e to the 2x. Okay, so what would u prime be then?
E to the 2x.
E to the
times
2x times 2, or 2e to the 2x. So y prime would equal 2e to the 2x over, that's the absolute value of u, right? So just e to the 2x again,
Well, should it?
and then
Oh,
the
but
square root, and is this u squared minus 1,
Yes.
right?
So would that be e to the 4x?
If you square this, if you square u, that would be e to the 4x
So
minus 1.
I don't think e to the 2x can ever be negative, but would you still usually want to keep the absolute value of that in there, so that way if it can be negative for a different problem, then it would be set to.
Yes, I would say keep that in there.
If you square it, why is x? Why is it just a t?
Sure. When you raise something that already has a power to another power, you just multiply those powers together. Just take, like, you had x to the 5th and you raise that to the 4th.
So it's 4x.
But 5 times 4 would give me 20 in that instance, right? So here, if I'm raising this to the 2nd power, I'd have e to the 2x in parentheses, raised to the 2nd power. I multiplied the exponents together, and if I take 2x times 2, 2x times 2 is just 4x. You're just multiplying. We don't know what x is, all right, but you've taken whatever 2 times x is, and you got another one of those, all right? So 2x times 2 gives you 4x.
And you can cancel the e raised to the 2x, right? You got 2 on top, 1 on bottom.
You got e to the 2x here, you got e to the 2x here. So 2 over the square root of e to the 4x minus 1.
Wait, we have to memorize all
Mm-hmm.
that? Why don't we get a sheet?
Okay,
That's what physics says.
that's
So
the way it goes.
I
Yeah.
think I got the.
this works for this one because e to the 2x power can never be negative. But would you be able to cancel them out if it was like x minus 2?
You had x minus 2 on top and x minus 2 on bottom?
Because
Correct.
on the bottom it would have to be.
That would, no, you probably won't want to do that then if it's still in its own absolute value bars.
Okay. And since this can never be negative, it doesn't matter. But
Correct.
for since we know that, would you want us to simplify it more, or would it be all right if we left it?
On this one, I'd like you to go here.
Okay.
Okay, so just some examples of doing some of the derivatives of these inverse trig. I want to go through the proof real quick of, let's do inverse cosine. Can I show you how it works? So, just kind of follow this here. So let's say we have just our regular cosine function, y equals cosine x. Alright? And we want to find the derivative of this function, y equals inverse cosine x. Okay? Well, this, you would agree, is the inverse of cosine, right? Okay? But so is this. When you were taught how to find inverse functions back in Algebra 2, what were my directions? Switch the x and y around and then try and get y by itself. That's kind of how we always found inverse functions. Okay? Well, I'm just going to switch the x and y around now. And so really, this function right here is saying the exact same thing as this is. One that just has y by itself and one doesn't yet. Okay? But I don't know how to do the derivative of this, but I do know how to do the derivative of this. Okay? I'm going to differentiate this function right here with respect to x. What's the derivative of x? 1. What's that?
Is this something we should write?
It might help you so then you don't have to memorize them as much. If you kind of know the proof on how to find it, if you're a little bit unsure. So in other words, if I'm going to differentiate both sides with respect to x, okay? So I get 1 equal, what's the derivative of cosine y?
Negative sign.
Negative sine y, but
d over dx.
times dy over dx. Because I differentiated with a variable that was not x. That's that implicit differentiation. Now if I solve for dy dx, I get negative 1 over sine y equals dy dx. I'm going to show you how we're going to change this here, okay? Bring back a little unit circle idea, okay? Would you agree that x squared plus y squared equals r squared?
Yeah.
Pythagorean theorem. Isn't your x value also your cosine theta?
Yeah.
And the y value is your sine theta?
Uh-huh.
And on the unit circle, we know that cosine squared plus sine squared equals 1.
Uh-huh.
Sine squared would equal 1 minus cosine squared.
Yep.
Sine would equal the square root of 1 minus cosine squared.
Uh-huh.
Square root both sides. And really, so sine of something is equal to the square root of 1 minus cosine. So now I could put in 1 minus cosine squared theta. But isn't cosine also just your x value?
Uh-huh.
So negative 1 over the square root of 1 minus x squared.
Okay then. I see how it
Crazy how
is.
man do that. Crazy on that, dude.
Yeah, I'm just gonna memorize them.
Yep.
I'm gonna go right in the corner.
We could prove the arc sine very similar. Okay? It would be the same exact process.
What about cosine or cosine?
I'm still thinking. For
Can't really use that use those for that bad boy.
For arc tangent, we know that tangent is sine over cosine, so I'm guessing it would involve some sort of quotient between the two of them.
See that?
And then once you know cotangent, or excuse me, tangent, you could probably do cotangent, very similar. I want to sit down and think a little bit more about that. I can't come up with it off the top of my head. So, honestly, as much as you use them, probably just good to have them memorized. They do definitely show up on an AP exam. We'll put them on a couple of or at least our next one for sure, maybe our next two. They'll show up on our quizzes, but you're just going to want to get them down. Honestly, if you look though, they're very much alike.
They have pairs.
They're in pairs. That's kind of how the book does it too. Sine and cosine are exactly the same except the cosine's negative. Tangent and cotangent are exactly the same except the cotangent is negative. Here you go. All the C's are negative. See that?
They all see in an arc.
They do all have an arc. That's impressive.
They all see. Why do they all?
You sure you shouldn't be in Calc 2?
I had to debate that myself.
I know. So whatever you need to help you memorize, that would be fine. Okay? If you turn the page to 378,
Who's that guy?
there are the 24 derivative rules you now know.
Elementary, yeah, right.
I don't know.
Okay?
Have you seen one?
You know all those.
I didn't do I? Elementary.
Yeah, that's a good.
Elementary.
I don't know L and A.
What is this? How is this elementary? This is not.
For elementary functions?
It's the basic pieces of it.
You're nope.